300 million light-years away, in a crowded neighborhood of the universe called the Perseus Cluster, there is a galaxy that shouldn't be visible at all. It has no spiral arms, no glowing core, no obvious edge. If you pointed an ordinary telescope at it, you would see nothing but black space. And yet, astronomers now believe this patch of apparent emptiness is a galaxy in its own right, one made almost entirely of dark matter, with barely a sprinkle of stars to give it away. They're calling it CDG2, which means Candidate Gas-Rich Dark Galaxy 2. And its discovery might be the closest we've ever come to catching one of the universe's oldest theoretical predictions red-handed. Welcome to Astrion X, and today we're diving into the hunt for dark galaxies, objects that cosmologists have expected to exist for decades but have never been able to prove. We'll look at why the universe should be full of them, how a team of astronomers finally tracked one down using 3 of the world's most powerful telescopes, and what it might mean for one of the biggest unsolved puzzles in physics. To understand why CDG2 matters, we need to rewind to the basic model cosmologists use to explain how galaxies form in the first place. According to the leading picture of the universe, known as lambda cold dark matter, galaxies don't start with stars. They start with dark matter. In the earliest moments after the Big Bang, dark matter, the invisible substance that outweighs ordinary matter in the cosmos by roughly 5-to-1, began clumping together under its own gravity. These clumps, called halos, acted like invisible scaffolding. Gas fell into their gravitational wells, cooled, and eventually collapsed into stars. Over billions of years, halos merged with other halos, and their embedded gas and stars merged along with them, building up the galaxies we see today, our own Milky Way included. It's an elegant model, and it explains an enormous amount of what we observe. But it has one nagging problem. The theory predicts far more of these dark matter halos than we actually observe as galaxies. Simulations of dark matter run on supercomputers routinely produce thousands of clumps around a galaxy like ours, at every size scale, all the way down to halos far too small and gas-poor to ever light up with stars. Only a small fraction of them appear to have gone on to build the star-filled galaxies that fill our sky. So where did the rest go? One leading explanation is that they didn't go anywhere. They're still there, quietly humming with gravity, invisible because they simply never had the material or the conditions to spark star formation. Astronomers gave this hypothetical population of starless halos a name well before anyone found one: dark galaxies. It's a strange kind of object to search for. A galaxy, by any conventional definition, is a collection of stars. A dark galaxy, almost by design, has none, or next to none. So how do you even begin to look for something that, true to its name, gives off essentially no light? For years, the closest astronomers came were hydrogen clouds. Neutral hydrogen gas emits a faint radio signal at a wavelength of 21 centimeters, and a handful of gas-rich objects with no visible stars, with names like Virgo HI 21 and Cloud 9, were picked up this way, floating in nearby galaxy clusters with nothing but gas and, presumably, dark matter holding them together. They were tantalizing, but never fully convincing. Gas clouds can be stripped from ordinary galaxies by collisions, mimicking a dark galaxy without actually being one. A new approach came from an unexpected direction: globular clusters. These are dense, ancient balls of stars, often containing hundreds of thousands or even millions of stars packed into a region just a few dozen light-years across, and nearly every known galaxy, including the Milky Way, has a family of them orbiting in its outskirts. Crucially, globular clusters are extremely bright for their size, which means they can be picked out at enormous distances even when the galaxy hosting them is otherwise far too faint to detect directly. That was the insight behind a 2025 study led by Da-Yi Lee, an astrophysicist at the University of Toronto. Instead of searching for stray gas or diffuse starlight, Lee's team combed through deep Hubble Space Telescope imaging of the Perseus Cluster, hunting for tight, isolated groupings of globular clusters sitting in otherwise empty-looking space. The kind of grouping you'd expect to see if a normal galaxy's globular cluster system existed with no galaxy attached. Using this statistical approach, the team turned up 10 previously known low surface brightness galaxies plus 2 brand new dark galaxy candidates. They named the more promising of the pair CDG2. A cluster of 4 globular clusters sitting close together isn't proof of anything by itself. It could be coincidence, or it could be the relic of a galaxy that was long ago torn apart. To make the case that CDG2 was a real, intact galaxy, the researchers needed to find its stars. Not the bright globular clusters, but the actual diffuse haze of a stellar population too faint to see on its own. That's where the second phase of the investigation began, bringing in 2 more observatories. Hubble's advanced camera for surveys had already resolved the 4 globular clusters with precision. The team then turned to imaging from the European Space Agency's Euclid Space Telescope, whose wide, deep, near-infrared surveys of the Perseus Cluster were, by 2026, mapping exactly this patch of sky as part of its ongoing dark matter survey, along with supplementary data from Japan's Subaru Telescope in Hawaii. Layered together, the data revealed something extraordinary. A faint, diffuse glow surrounding the 4 star clusters, providing strong evidence of an underlying galaxy. Even more compellingly, the diffuse light picked out independently in the Hubble and Euclid images matched almost exactly, which ruled out the possibility that either team was simply looking at an imaging artifact or an instrumental quirk. 2 completely different telescopes, using different optics and different wavelengths, we're seeing the same faint smudge of starlight in the same place. As Lee put it, this marked the first time a galaxy had been detected purely through its population of globular clusters, found not by spotting the galaxy first and then noticing its clusters, but the other way around. Once the team had confirmed the galaxy's existence, the next question was how much of it was actually dark matter. The numbers turned out to be staggering. CDG2 as a whole shines with roughly the light of 6 million sun-like stars, a rounding error compared to the hundreds of billions of stars in the Milky Way. Of that already faint total, the 4 globular clusters account for somewhere around 16% of all the visible light, a genuinely unusual ratio. In a typical galaxy, globular clusters make up a vanishingly small fraction of the total starlight. It's as if you tried to weigh a person and found that their fingernails accounted for 1/6 of their body mass. Piecing together the light budget with known relationships between globular cluster populations and the size of a galaxy's dark matter halo, the researchers estimated that dark matter makes up somewhere between 99.94 and 99.98% of CDG2's total mass. And if its globular cluster population follows the more typical pattern seen in other galaxies, that figure could run even higher, essentially indistinguishable from 100%. In other words, if you could somehow weigh the entire galaxy, ordinary matter, stars, gas, dust, everything you or I are made of, would barely register. That places CDG2 among the most extreme dark matter-dominated galaxies ever identified, edging out even well-known ultra-diffuse galaxies like Dragonfly 44, which had previously held a similar reputation. CDG2 is still labeled a candidate rather than a confirmed dark galaxy, and the astronomers behind the discovery are the first to say so. The evidence is compelling but indirect. Nobody has yet measured the motion of individual stars within it to directly confirm the mass implied by its gravity. Follow-up observations, likely from Hubble, Euclid, and possibly the James Webb Space Telescope, will be needed to nail down the case. But if it holds up, CDG2 does something remarkable. It turns a decades-old theoretical prediction that the universe should be littered with starless dark matter halos into something astronomers can actually point a telescope at. For a phenomenon that, by definition, gives off almost no light, that's no small feat. It also hints at how many more of these objects might be hiding in plain sight. Lee's own statistical search flagged a second promising candidate, CDG1, alongside CDG2, and the same globular cluster technique could in principle be applied to every galaxy cluster within reach of Hubble and Euclid's cameras. Recent simulations of our own cosmic neighborhood suggest dark galaxies should be scattered throughout the outskirts of galaxy groups like our local group, mostly in quiet, low-density regions where gas never got dense enough or hot enough to catch fire into stars. Euclid, for its part, is only getting started. Having launched in 2023, it is now steadily mapping more than a third of the sky in painstaking detail, building the very survey of dark matter's gravitational fingerprints that made spotting CDG2's faint halo possible in the first place. Its first full cosmology results are expected in 2027, and if a single, almost accidental cross-check between 3 telescopes was enough to confirm one dark galaxy, it raises an interesting question. How many more are sitting in Euclid's data already, waiting to be noticed? For now, CDG2 stands as a reminder that some of the most significant objects in the universe are also the hardest to see. Not because they're too far away or too small, but because, almost by their very nature, they were never meant to be seen at all.